Hi friends, this is Ganesh. Welcome to my channel. In this video, I am going to say about FPGA architecture, and so many members have doubt why we are doing synthesis, why we are doing implementation, and why we are doing bit stream. For every question, I will give answer in this video. Before going to the answers of the following things, first we will discuss some basics related to FPGA architecture. Mainly FPGA architecture contains four things. First one is logical block. Logical block, which we can program that block, okay, which is indicated with brown color. All brown color things are logical blocks, which we can be programmed. And another one is, next one is switches. Switch block. Switch block is nothing but it will support for connection between this block to this block with help of some interconnections. Okay, this can be also programmable. This switch box is also can be programmable. And next one is interconnections. Interconnection means nothing but connection by connection wires. Okay, it's not a big one. And I/O pins. Either these pins we can use as input pins as well as output pins. Now we will go through the logic block. What thing is present in the logic blocks? Let us discuss. If we take logical block or configurable logical block contains majorly these three components. Additional some gates may be used. Majorly these three are the main component. Lookup table. LU2 means lookup table, and D means D flip-flop, and this one is mux. If you are designing combinational circuit, this lookup table and this lookup table output is directly will be applied to the output of mux. If you are developing the sequential circuit, then output of lookup table is passed through D flip-flop, and this D flip-flop output will be present at mux output. You got my point. What I am trying to say is, if it is combinational, mux will accept this directly lookup table output. If it is sequential, mux will accept the output from D flip-flop. In logical block, these type of blocks, these type of lookup table blocks will be present two number of this type of blocks will be present in each logical block. This is the basic diagram. Additional with this one, some gates will be used. Some gates will be also used. Till now we have discussed about basic FPGA architecture. This is the very basic FPGA architecture. Nowadays we are using is advanced FPGA architectures, not these things. Advanced FPGA architecture and basic FPGA architecture. What is the difference means? Same structure, along with this one, some more elements are added. Example, DSP slicers, or on-chip memory, or like a PLL block for clock, etc. things are added in advanced FPGA architecture. Let us see some of the examples of FPGAs. These are the FPGAs. Spartan 3 FPGA, which is from J-Links, and Spartan 3, Spartan 6, Vertex 5, Vertex 7, and Artex. These are the some of the examples for FPGA. Now we will come to our board, Nexus 4 DDR board. In Nexus 4 DDR board, they are using Artex 7 FPGA. Artex 7 FPGA. In that board, the following features are available. First feature is 15,850 logical slicers. Logical slicers means nothing but our CLBs. 15,850 logical slicers are available, and each slice contains 6 input lookup table and 8 flip-flops. 6 input lookup table and 8 flip-flops. When it is a logical, then it will use only lookup table, some logical gates. When it is a sequential circuit, then it will use 6 input lookup table, some logical gates, and this 8 flip flops it will use. Other than that one, 4860 KB of fast block RAMs are available. Means nothing but on-chip RAM is available. Why on-chip RAM is required? Actually, FPGA is a volatile device. When power is off, that program will be lost. Okay, if you store program on this RAM, okay, if you store program on this RAM, okay, when you switch on the FPGA, automatically this RAM will, the program will be loaded from this RAM to FPGA. That is the advantage of this RAM. And next one is PLL. PLL will provide clock. 6 clocks are available from this PLL. 6 different clocks we can generate from this PLL. And next one is DSP slices. So many members DSP slices means discrete signal processing. I think you are already familiar because you have the subject of DSP. And 240 number of DSP slices are also available. And on-chip ADCs are available. Now this FPGA deals with only digital signals. For that purpose, analog signal must be converted into digital. For that purpose, on-chip ADCs are also available. This is the total features of RTX 7 FPGA. 15,850 logical slices and 4,860 KB of fast RAM and 6 PLL and 240 DSP slices and on-chip ADCs are available on FPGA. Now we will discuss about synthesis. This is the definition of synthesis which is given in Wikipedia. I don't want to discuss about this one. I want to say this synthesis, what is meant by this synthesis in simple words. In my view, synthesis means converting the HDL code, means this code, into logical diagram. Convert this HDL code into logical diagram, and that logical diagram is developed using CLBs what are available in FPGA. The CLBs what are available in FPGA. Here one example I have given. We have, by seeing the logical diagram or truth table, we have written the code for full adder, and again after synthesis you are getting like this. In this case, this logical diagrams are same. But if we go to the counter program or any other programs, here logical diagram and here synthesis diagram, both will be not equal. Here logical diagram, after synthesis we are getting one logical diagram. That logical diagrams are both are not equal, because what code we have written, that code is converting into logical diagram based on the CLBs available on FPGA. What synthesis tool will do means, what statement you are writing, that logic will be converted into the logic diagram or RTL diagram by using what CLBs are available in FPGA. CLBs are having lookup table, some logic gates and flip-flop and mux. These are the things. Now let us discuss one more example. 4-bit up counter. This is the logical diagram of 4-bit up counter. Now from this one we will write the code for up counter, and that after synthesis, that code will be converted into in this manner. Now you can see here, this logical diagram and here diagram both are different, because that is logical diagram normally what we know. This is also logical diagram, but converted using CLBs. What elements are available in CLBs? This diagram is developed using CLB, means what elements are present in CLBs. If you see here, D flip-flops are 4 D flip-flops it is taking, and this D flip-flop output is every time incrementing. This one is adder. This one is one adder. Okay, every time it is incremented by adding the logic 1 to that previous output. So every time it is adding logic 1 to previous output. This is the logic synthesis tool solved according to the components available in CLBs. These two are entirely different. After synthesis, you can see the some results like this. Okay, how your logic, how many lookup tables are utilized, and your logic, how many registers are used, your logic, how many mugs are used. You can see in this report, and actually how many are available on FPGA. Those aspects you can see here, and how much percentage you have utilized. Those aspects you can see here. Okay, in my full adder case, it is using only one lookup table, and out of 63,400 are available. Lookup tables are available. Okay, only one lookup table is used. Okay, means 0.01% we have utilized, and memories are not used, registers are not used, latches are not used, mux are not used. This is the outcome of synthesis. Our logic will be converted into RTL. Okay, register transfer level. Okay, based on that elements available in CLBs. Okay, for your logic, how many lookup tables are utilized, how many memory elements are used, and how many registers are used, marks are used. Okay, this report will be provided with synthesis. Now we will talk about implementation. From after synthesis we will go for implementation. What implementation will do means, this logic what we have developed, that logic will be transferred to FPGA. Okay, that logic will be transferred to FPGA. And what implementation tool will do means, okay, the connection between two logical blocks, and the connection between the two means IO to logical blocks, those aspects will be dealt by implementation. It will provide, the implementation tool will provide the optimum routing between the two logical blocks and IO ports to logical blocks. Optimum results it will provide. Along with that one, some outcomes are coming from implementation tool. After synthesis, the following reports are available: utilization report and Vivado synthesis report. After implementation, following reports are available. One thing is post optimum design DRC report. DRC means design rule check. It is checking whether we are violating the design rules or not. And here you can see, okay, place the design, where we have to place, and what IO ports are utilized. Okay, IO port report, utilization report. Same way, you can see route design. You can see here so many things: power report, routing status report, timing summary report. So many reports it will provide to us. According to your view, which things are required, you can see that following values. Let us talk about bitstream. What bitstream will do? Bitstream will convert our design. Bitstream will be convert our design to bit format. Why means FPGA can understand only logic 1, logic zeros. For that purpose, this our design will be converted into .bit file. FPGA can understand only bit file, not our Verilog code or VHDL code. It can understand only the .bit file. So the bitstream will convert our design into .bit file. And after converting this bit file, and hardware manager is used to send this file to that kit, Nexus 4 DDR board. Now this bit file will be sent to FPGA Nexus 4 DDR board using hardware manager tool. Let us see the overview of complete design flow. First, what we are doing, we are taking either logical block or truth table. We are writing in our Verilog code, and that Verilog code is converting into logical diagram again based on the CLBs and what components are available. Based on that one, it is converting that code into logical diagram. After that one, we are transferring this logical diagram to our FPGA. Okay, and this implementation tool, what it will do, it will provide the optimum routing between two logical blocks and optimum routing between logical blocks to IO ports. And finally, what it will do, bitstream will do convert this our design to a bit file, because it will my FPGA can understand only bit file, logic 1 and 0 1 0, and this bit file will be sent to a Nexus 4 DDR board using hardware manager. This is the complete overview of our FPGA design flow.